Okay, so today is a pretty cool day. So, we're going to talk about something that's kind of one of the goals of the class, okay? And we're going to be talking about different size infinities, okay? So, yeah, okay, so okay, and the code word for this is cardinality. All right. All right, so there's kind of a couple ways that we can approach this topic. So one way that I could do it is I could do it how the book does it, where they line it out and they start developing the theory, right? And then at the end, they get to kind of the fun statements, okay? So I decided against that because it's not as fun, okay? What I'm going to do today is I'm going to kind of give you a less rigorous version of the theory right now, but to a point where I can explain to you the ideas and make some fun claims, okay? So, okay, so here are the outrageous claims of the day. All right. The first one is that there are different size infinities. Okay. Are different size infinities. And in fact, there are an infinite number of infinities. All right. I don't know if I'll get to that part yet, but I wanted to tell you that that's true. Okay, so the goal is to start talking about infinity and start talking about counting in a more serious way. Okay, so 2 is that so the rational numbers Q are the same size as the natural numbers. Okay? And the third thing that I want to say is that the real numbers so it's kind of like the number of real numbers so are strictly larger than the naturals. Okay, so this is the real numbers here. Okay, so these are outrageous and they're true things. Okay, and I need to say, so really I'm talking about like the number of real numbers, and there's kind of ways to count them. And this is what everything today is going to be about counting. Okay, so we need to talk about how to count. And let me just say that this is due to Dedekind and Cantor. So these ideas. This appeared in a paper of Cantor's. So I told you that they were really good friends, right? The definition of an infinite set is due to Dedekind. And then 2 years later, this paper of Cantor appeared. And this is, so one was in 1872. And then in 1874, the same year that Cantor got married and visited Dedekind on his honeymoon, right? I told you guys that before, that they had like a little bit of a bromance. That Cantor published this paper which includes these 2 facts. Okay? All right. So to talk about that, I really need to talk about this thing called cardinality. So let's start over here. So here's a little subsection. Now I'm going to just start talking about how we count things. So how do we count things? Okay. Okay. So I'm going to ask you guys a question. Okay. So here's a hypothetical situation. So suppose I don't know anything about numbers, okay, and I have a theater, okay, and in the theater there's a bunch of empty seats, and outside the theater there's a crowd waiting to come inside the theater, okay. How can I determine if everybody will fit inside the theater? Does anyone have an idea? Any idea is fine. Yeah.
If there are more seats than people.
If there's more seats than people, and then how would I do that? So, like, how do I determine if there's more seats than people?
Put all the people in them and see if there's any empty.
Exactly. So you put all the people in the seats. You tell everybody, okay, everybody go inside, right? And you sit down. And if there's leftover seats, right, then there's not enough seats. There's not enough seats for the people, okay? But this idea, so my friend Leo told me to do this, and I did this in the previous class, and someone made the exact same suggestion. But the idea is to use bijections. So when you're doing that, what you're really doing is you're setting up a bijection between the people and the seats, right? Another suggestion that someone said is take a penny from everybody, right, and then go put the pennies on the seats. That would be establishing a bijection between the pennies and the people and the pennies and the seats. Okay, so when this happens, we say that when everything fits, we say that all these sets have the same cardinality. So the people have the same cardinality as the chairs, have the same cardinality as the pennies. Okay, yeah.
Isn't that how tickets work? Essentially,
Yeah, that's how tickets work. Right.
Instead of pennies, you now have tickets, and each ticket corresponds to a certain seat.
Yeah, that's the idea. So we're setting up tickets. Tickets are a function, right? And they assign people to seats. Okay, so so the idea that we have is to set up bijections between sets. Okay, so what's a bijection? So let's recall what a bijection is. So a bijection So let's recall a bijection is a function f from s to t that is injective. That's the same thing as one-to-one and onto. And surjective. That's the same thing as onto. Okay? So, all right, so equivalently, F is a bijection if and only if it has an inverse function. Okay, it has a left and right inverse function, and when you have a left and right inverse, right, then they're the same thing. Okay, so this is something that we talked about. All right, so so now I'm going to give you the definition of cardinality. So what we're going to do is we want to count things. Okay, and so the way we're going to count things is that we're going to set up bijections between sets. Okay, so two sets which are bijective, meaning that there's a correspondence between them. Right, we're just going to treat them the same way. All right. So, and when they when they're in bijection, we'll say that they're equivalent. Okay. So, so let me just give you the definition. So let S and T be sets. Okay. So S is equivalent to T. And so we say, and this is the notion that I'm defining. S and T have the same cardinality right? Okay, so let me just get rid of the quotes there. So this is the equivalence relation if and only if And so this is the part that I'm defining. I'm going to define this side by over here. If there exists a bijection f from S to T. Okay? So this looks a little anti-symmetric because I'm saying that f goes from S to T, but we have an inverse function. So if you have a bijection from S to T, the inverse function will be a bijection from T to S. Okay? You can actually compose bijections to get bijections. If you have two bijections, you can compose them to get bijections. And so there's an exercise in the homework that I'll just have you guys check, is that this, so the notion of having the same cardinality is an equivalence relation. Okay? So let me give you some notation too. So, okay, so I'm going to say something. So an equivalence class, so notation. The equivalence class of a set under this relation is denoted by this of a set, let's say S. Okay, so this is all the sets which are equivalent to it. Okay, so this is, and sometimes we call the class is the cardinality of the set S. Okay, so so this is a thing. Okay, so we have to fix like a set of sets, and then we define the equivalence class on this set of sets by defining this bijection thing, and then we call these things class. And so these classes will play the role of infinite numbers, or they'll play the role of numbers. In particular, we'll be able to get infinite numbers from this. Okay, so the idea is that so the idea is we use certain sets, standard sets, to measure the size of other sets. Okay? So let me give you an example. So let me give you some notation first. So they'll fix n in the natural numbers. Okay, and then this set here, this will be 1, 2, 3, 4, all the way up to n. Okay, so this is an n-element set. Okay, this is a subset of the natural numbers. This is just an n-element set. Okay, so this is one of our standard sets that we're going to use. Okay, so examples of standard sets. Okay, so here n sub n is one of them, right? So any set, well, let's see. I'm getting too low here? Okay. So any s equivalent to n, right, is said to be of cardinality n. Okay? So okay, so really n is supposed to be the equivalence class, but like we're just going to write for this one since these classes are supposed to be numbers, right, we're just going to write n for this class. Okay, so let me give you an example. So like a kind of a sub-example. Okay, so n sub 4 here, this is just 1, 2, 3, 4. Okay, and S could be the set A, B, C, D. Okay, and n sub 4, so this 4-element set is similar to this set here. They're equinumerous, or they have the same cardinality. Or we say this thing is equal to this thing, so they have the same equivalence class. Because they have the same number of elements. Okay, so here we have these things. This means the same thing here, because we can write a bijection. So f of 1 could be A, f of 2 is B, f of 3 is C, f of 4 is D. So this map is injective, right? No two guys map to the same thing, and it's also surjective, right? This thing is a bijection. Okay, so these things have the same cardinality. This has cardinality 4. Okay, we say it's a set of cardinality 4. Okay. So any questions so far? Yeah.
So you say the class is the cardinality. So for the standard set n of n, the class of
The class of
of S is n.
Yeah. So we make an abusive notation, right? The abusive notation is we identify natural numbers with the cardinality of the set of natural numbers up to that number. Okay? So it's like, so n element sets have cardinality n. Okay? That's the idea.
So the cardinality would be the number of elements?
Yeah, the cardinality is the number of elements.
So
Yeah, it's kind of like length, but I'm going to throw a wrench in that right now. Okay? Yeah. So, but it has to do with bijection. It's the size of the set, and it's one notion of the size of the set. So we want to be able to talk about one set having more elements than another set. Okay? So let me give another example. So this was like our first example here. This big bullet here with this sub-example. Now we're going to do another one. So another standard set here is the natural numbers. 1, 2, 3, 4, like so on. Okay, so all the natural numbers. So any S equivalent to this is said to be B of cardinality. Okay, and now I'm going to introduce a new letter. So this is Aleph naught, or Aleph 0. This is the Hebrew letter for A. Okay, and so this is like the first infinite cardinality. So here, the size of the natural numbers is this weird new letter that we call Aleph naught. Okay, so this is the idea is this is the first infinite cardinal number. Okay, I'm going to give two definitions, and then I'm going to give some examples of this. All right? All right, so let me first give the two definitions. So we have like 1, 2, 3, 4, whatever. And then we have this new cardinal number, which is the cardinality of the natural numbers. Okay? So definition. So a set S is countable if and only if, so this is the definition, it can be put in bijection with the natural numbers, or n sub n for some n, or the natural numbers. Okay? Let me give you a definition. A set S which is not countable is uncountable. Okay, so we have these two definitions of countable and uncountable. Countable has a cardinality like this, or one of those natural numbers, right? And uncountable is something that's like bigger than this. It can't be put in bijection with one of these sets. All right, that's the idea. All right, in the beginning of the class, I said that the rational numbers were countable and the real numbers were uncountable. All right. Okay, so let me give you the definition. So this started from, all this stuff started from what Dedekind, so like they were looking for a proper notion of infinity. And people were thinking about infinity for a very long time in different contexts. In this context of counting, this was due to Dedekind in, this definition is due to Dedekind in 1872, okay? 2 years before the honeymoon, okay? And I think Cantor was 26, and he's like 10 years older than Cantor, okay? So he said the following. So a set S is infinite, okay? If and only if it can be put in bijection with a proper subset. Okay, so let me just make this a little more clear. So what I'm saying is that there exists some S prime, i.e. there exists some S prime which is a subset and not equal to S, such that S prime is equinumerous with S, or they have the same cardinality. I could have written absolute values and equals there, and the same thing. Okay? Subset but not equal, right? A proper subset means subset but not equal. Okay, so now I'm going to come back to this thing and give you some examples of things which are equinumerous with the natural numbers. Okay, so there's a notion of size, but you should only think about the size up to a certain thing. So like, okay, so let's think about like the even numbers. Okay, would you say that there's more or less? So the even numbers, are they bigger or smaller than the natural numbers? Well, I would say, in one instance, you could say that they're smaller since they're a proper subset, right? There exists a natural number that's say, an odd number that's not an even number. That's one way of doing it. But that's not the notion that we want to think about today. We're only thinking of things up to ability to put in bijection, okay? So, so this is an example of a set that can be put in bijection with the natural numbers. So let me give you some examples of countable sets. And in particular, sets of cardinality aleph naught. All right, this thing. Okay? So let me underline this. I guess this is kind of long-winded, but okay. But let's do this. The even numbers are countable. Let's do even positive numbers. But it's true for even numbers in general, even integers as well. Okay? So let me show you the bijection. Okay? So I'm just going to write it like this. So 1, 2, 3, 4, 5, 6. Okay, so these are the natural numbers. Okay? And the even numbers, I'll write it like this. So this will be 2, 4, 6, 8, 10, 12. Okay? And the map goes like this. This guy maps to this guy, 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 this guy maps to this guy. Okay, although this is a proper subset of this, right, this can be put in bijection with this set. Okay? The map here, it's onto, right? Every even number gets hit, and it's 1-to-1. No number maps to the same even number. Okay? So these two guys have the same cardinality. Okay? And this shows, under Didekind's definition, that the natural numbers are an infinite set, because it's a bijection with a proper subset. The even numbers are a subset of here, right? And it's a proper subset. You won't be able to do this with finite sets. And so that's something that we need to like prove. Okay? And so this is why I was saying like we could either start to develop the theory, right? Or we could do the fun part, right? And so we'll worry about that later. Okay? But for right now, right? This is one example here. Okay? So let's do another example. So the odd numbers. The odd numbers are a countable set. So the positive odd numbers are countable. Okay? So let's set up our bijection again. Here's the natural numbers, and then I'm going to do the odd numbers, like I'm going to call them O. Okay? So 1, 2, 3, 4, 5, 6, and then this is going to go. I put 3 dots when I want it to keep going. All right? And then 1, 3, 5, 7, 9, 11, and so on. And the map goes like this. Okay? So, all right. So note that I have to put things in a sequence, right? So if I can just make a sequence and I can count them, then they're countable. So the definition makes sense. Okay? So if I can just make a list of all of them and all of them appear. Yeah?
Does the sequence need to be in order?
Yeah. What do you mean?
So in other words, odd numbers, I'm thinking about the rationals in the reals, like they wouldn't necessarily be in order, but you can count them.
Mm-hmm.
So does the bijection have to go from smallest to largest?
No, it does not have to go from smallest to largest, and that's the idea of Cantor's. That's one of Cantor's ideas, right? That's the point, right? Okay. So all right. So yeah. So there is no largest odd number. There is no largest odd number. Yeah, we can count. Every odd number appears. Give me an odd number. There's no largest odd number. So for every odd number, if I add 2 to it, I'll get a new odd number, which will make it another larger odd number. Yeah.
If you were doing like, I don't even know if this is possible, but like all odd numbers, would that be countable? Because like, would you have a starting point? Like, there's no starting nor ending point, so like, how would you know where?
Yeah. So let's do another example. So the even. So that's the point. Is that the dots are hiding something. Okay. So like the integers. So z, we usually write this as ... -2, -1, 0, 1, 2. So these are countable. right? To show that they're countable, I need to put them in bijection with the natural numbers. So here, I'll make a list. 0, 1, minus 1. 2, minus 2. 3, minus 3. And this is maybe what you were talking about. Does the order matter? The order does not matter. We don't care. We're not viewing these as ordered sets. We're just viewing them as sets. Okay, so we consider them with no extra structure. All we care about is elements and functions. Okay, so yeah, we don't care about the ordering at all. All right, and so this establishes a bijection between the natural numbers and this set. So 1 maps to 0, 2 maps to this guy, so on and so forth. Notice that I could like switch these. Right? It doesn't really matter. What really matters is the behavior for very large things. Okay, so I could permute these or something like that, and I'd still give a bijection. All right? Permute means flip around. Okay? All right. Okay. So so let me give another example first to give you another infinite set. So the real numbers are another example of an infinite set. Okay, so let me give you the crazy claim. And this is what I'll prove later. So this is the first theorem that appeared in this 1974 paper, or the first theorem that I'm stating. I don't know the order of the actual paper. But the first claim is that Q is countable. Okay, so that I can make a sequence of numbers, and I can put them in sequence so that every single rational number appears once, right? And I can write out a list, and in this list, every rational number will appear. Okay? It's like a magic show. Okay. If you've never seen it before, I thought this was the coolest thing ever. Okay? So let me give you another example of an infinite set. So these are countable ones. So it turns out the other claim was that the real numbers are uncountable. So another example of an infinite set. And I'll come back to this. Okay? Another infinite set. Okay? According to Dedekin's definition says a set S is infinite if it can be in bijection with a proper subset of itself. Okay? So R is infinite. Okay? And here's the sketch. Okay? So what we'll do is, well, I'll literally draw a sketch here. Okay? So we will establish, we will put R in bijection with -1 to 1, which is a subset not equal to R. Okay? And so let me show you how to do this. Okay? So here's the real line. Okay, here's 0. And I'm going to take the point here. Let's take the point 0, 1. Okay, so this is in the xy plane. Okay? And then I'm going to make a circle here, a semicircle, like so. Okay? So this thing has this is a semicircle of radius 1. Okay, and so what I'm doing for you is a cartoon. It's not a proof. Okay, so but what I'm going to do is I'm going to show that the semicircle. So let S be the semicircle. Okay, so there is a map from the semicircle to the real line. Okay, and so what it does is it takes a point on the semicircle, right? And it draws the line between this point and this point here, and then it connects the dot and maps to here. So we'll call this map here, if this is called A, this thing will be f of A. So f is a map from S to the real line, right? given by this drawing a line between this point here, A, an element of S. So A is an element of S. Right? This is S here. S is the smile thing. Okay? We take this point here, and we map it here. All right, maybe I could have written this as a tuple, like as a pair of things, but I'm just going to write it as an abstract element. So A is really, note that A is equal to like x1, y1 for some xy. These two guys are reals. Okay? So I'm just really going to write it as a single thing here. Okay? So, but this is the map here. It takes this thing and it maps it to this thing. And the way that I determine this guy is I make a line through here and here, and it intersects this line. Okay? So this is a bijection. This guy is a bijection. Okay? So these points here are excluded. Okay? All right. The other way to do this is that I have another map here, G. Okay? And this is really the interval -1. So this is -1 to 1. So here, there's this projection map where I just take A and I map it down to this line here. So this is the map G. Okay? So we have this G from S to R. This is also a bijection. So this projects, so G of A, so this is G of, let's say, like x1, y1. And so this is really like, it just sends the x coordinate here. Sorry, not to R, to this interval, -1 to 1. Okay? So, okay, so this is a bijection, this is a bijection. And so the bijection between the bijection between that interval and the real numbers is given by, so between -1, 1, and the real numbers is given by, okay, so here I'll do G inverse, and then I'll do F. So G inverse composed with F. Okay, so the composition of bijections is bijections. And because it's a bijection, it has an inverse function. All right. So this shows that there's a bijection between R and a proper subset of itself, right? Which shows that the set's infinite. That's all I was showing there. Okay, so this is an infinite thing. Okay? All right. So all I did was I just cooked up some map, which is a bijection. So you can see that it's a bijection because from visually, right? No A maps to the same guy here. Also, no A maps to the same guy here. So you can just do that. Yeah?
So we say that R is an infinite set, and we said that the natural numbers were an infinite set.
Yeah.
But we said that the integers Z are countable. Can an infinite set be countable?
Yeah, it's countable. The natural numbers are countable, right? That's the definition of countable, if it can be put in bijection with the natural numbers. My claim now will be that the rational numbers are uncountable. Okay? Or sorry, the rational numbers. The real numbers are uncountable, while the rational numbers are countable. Okay? So that's my claim. That's the crazy claim of the day. Okay? Those are the two crazy theorems. Okay? So you guys ready to see those? Other questions now before I get to it? Okay. Okay, so, yeah.
There is no negative where is this, so where is the bijection?
So -1 here?
Huh?
What did, excuse me?
I mean, there is no negative y.
-1.
Yeah, it's not subjective because there is only positive y. We'll see that.
You mean here?
Yeah, I mean,
So really G, so I made another copy of the real lines. Do you guys understand that I made another copy of the real line here? So this is really a replacement for like this subset here. So I could really project this back down if I wanted to. Okay? but yeah, we're excluding these endpoints here because if I went out to here, we would need some other concept of negative infinity, which you can't make sense of, but it has nothing to do with what we're talking about. We're talking about counting right now, okay? So, but if I tried to make this a map from, say, like this point over here, way out here, right? It would see how this line gets all the way up like this, and it would send that thing way out, okay? Yeah.
And there is no negative consequences exist. Also, there is some numbers under x-axis.
I don't, so maybe you can ask me after. Okay, yeah.
Could you just clarify, like I follow you all the way through just in your literal last line where it's like.
This part here?
Yeah.
So in order to go from this interval, so we're interested in like this interval here, right? So I really define functions from this set here and this set here, right? So in order to go from this line to this line, right, what I have to do is I have to go backwards. That's the G inverse. And then I have to go here, right? That's what I wrote down, right? And that's what gives me the bijection between those two things. Okay. All right. So great. All right. So now let's do the crazy theorems. So this is the claim that I did here. So the first claim is that I will be able to write down a sequence of the rational numbers, right? So the first claim. So the big theorems. Okay, so the first theorem okay, so this is from the 1974 paper, or not 1874. This is due to Cantor, the same guy. So Dedekind and Cantor were the set guys, okay? So, and it made everyone really uncomfortable, is that Q is countable. Okay, i.e. there's a bijection between, so it's not a finite, obviously it's not a finite countable, right, but it's an infinite countable. There's a bijection between Q and the natural numbers. Okay, let me show you this proof. So in the proof, so we will first show a bijection between the natural numbers and the positive rational numbers. All right? And here's how it goes. Okay, so I'm going to write down the rational numbers. 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, okay, 6 over 1, and then this keeps going. Okay? 6 over 1, yeah. All right? So now I'm gonna do this 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, 6 over 2. Okay, you guys get what I'm going to do now? 1 over 3, 2 over 3, 3 over 3, 4 over, this isn't the sequence, by the way. 4 over 3, 5 over 3, 6 over 3. This keeps going, this keeps going. Okay, let's do one more row. 1 over 4, 2 over 4, 3 over 4, 4 over 4, 5 over 4, 6 over 4. All right, I want to do one more row. Kind of didn't space this out well. Let me try and do it here to see if you guys get the pattern. Okay, so here is how this is going to work. Yeah?
So like, could you write this any way in terms of like dividing by like an equivalence class, or like a modular of the natural numbers? Or just, like,
So are you asking like
the natural numbers divided by like mod n, like mod n, like where n is a natural number?
So, I mean, we are separating them into the things, well, they're divisible by certain denominators. I mean, we are breaking up into certain denominators. So let me just continue and then see where we're going here. Okay, so this is the first number, 1. Okay, so here's the sequence. I'm leaving space here in case I need another row. Okay, so 1. So that's the first number. The second number is going to be a half. And the other one's going to be 2. So we go like this. Now I'm going to loop around and go this way. Okay? So, and then I follow this down. Okay? And so then I'm going to come back up again. Okay? So let me continue this thing. So then we have 3. Okay? 2 over 2 already occurred. So we skip this. Okay? So we're going to skip this one since it's the same one as this. Okay? So we skip it, and then we're just going to go to 1/3. Okay? And now we're going to continue. 1/4, right? 2/3, 3/2, and then 4. Okay? So let's continue this way. So this is 1/4, 2/3, 3/2, 4 over 1. Okay? And then we're going to go around again. Okay? So we have 5. We have half. We are going to skip this one. Okay? Because it already appeared. It appeared as 1/2 here. Okay? Oh, sorry. It appeared as 2. Sorry. It appeared as 2. Right? Okay? And then we're going to skip this one. That's 1. Okay? And then we're going to skip this one. It appeared as a half. Okay, and then we have 1/5 up here. So let me do 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, and it keeps going. Okay, so then it comes back down here, and we go this way. So we're down off the board, and then we come up there. You see where we're going here? Okay. So then we have 1/5. So where are we? We're 1/5 down here. So I guess we do need one more. So we have 1/5. It comes down like this. Sorry, 1/6, 4/6, 5/6, 6 over 6. Okay, you guys see how it goes? And then so I really needed 2 more rows to keep going. Okay. So did I write this one down? So we have 5. Then we skipped a bunch, right? And then we eventually got to 1/5, right? You guys see how that goes? All right, and then I'm going to continue this. But the way that we continue is we go down and we go back around. And then eventually, we're going to come up here till we get to 6. And then we go up and around again. Okay? And then every time we have a repeat, right? Every time we have a circled one, we skip it, right? So we make this diagonalization. So we make the sequence. By this Cantor, what's called, this has a name. This is so important, this proof technique here, where we had all these ... dots, right? And somehow we eliminated all the ... dots to get a sequence where we only needed one ... here, right? That's the point. Like, just like how we had the integers, they had 2 sides, right? Well, this thing had tons of sides to it, right? And it was a very clever trick using the sequence by this Cantor diagonalization. Yeah, Tyler?
So if you rearrange those terms, won't you just get all q greater than 0?
Yep.
And the order just doesn't matter?
Yeah, the order doesn't matter. We don't care about the order. We only care about that all the numbers appear. And if you notice, a rational number, if we take this table out forever, every rational number will appear somewhere, right? It has a denominator, right? So eventually, we're going to wrap around, and we're going to get to that rational number, right? It's crazy cool. Yeah.
Is there a reason for going down versus over in the diagonalization?
Like, why didn't we just go this way?
Well, no. Like, why not go 1, 2, 1/2, 1/3.
No, it doesn't matter. No. You can. There's plenty of ways to do this,
Just
right?
as long as you include everyone.
Yeah, as long as you include everyone. And actually, I have no idea to the extent to which, I presume someone has done this, but I don't know the extent to which, like, what are all the ways to count these? I'm not sure what the answer to that is. But that would be an interesting question to think about, for example, right? But yeah, you just go like this and you wrap around and you see, you can do this, right? Like, I don't know what the best possible, like, closest to order preserving thing there is, if there is such a notion, or if you can get arbitrarily close or things like that. I guess I don't know, all right? So yeah, so this is the argument here. So this shows this bijection, okay? And so to finish, so let's see. So we skipped, remember, we're skipping all the circled things, right? So to finish, the sequence for Q, we can just alternate between sequences like this for positive and negative. And negative. Like we did for Z, right? But there's one thing that I forgot to say, right? We have to throw in a 0 somewhere. So you can maybe start with 0 and then proceed to do this thing. You could do, you'll have this sequence, you'll have a positive version of this sequence and a negative version of this sequence. And you just jump between those two sequences. Yeah?
Do you have like an entire line above that? Like, I know it'd be silly, but just have like 0 over like 1.
Yeah, you could do 0. Yeah, that's one way you could do it. That's another way you could do it. You can make the 0 sequence here, and then you go through. All right. So what am I at right now? 3 minutes, right? Or no, it's over. OK. OK, so next time, let me show you. Well, OK, next time I'll do the uncountability of the real numbers. OK, so I'm going to show you that for any sequence that we cook up of real numbers, I'll produce a number that is not in that sequence. So it shows that it can't be put in bijection with the natural numbers. All right.